What's up, science fans, and welcome back to Summarize Science. Today, we're looking at a fascinating piece of high-speed propulsion tech, the solid-fuel ramjet, or SFARJ. Think of ramjets as the simplest jet engines imaginable. They have no moving parts and only work at very high speeds. Using solid fuel makes them even simpler and more compact, perfect for things like long-range missiles. But this simplicity comes at a cost. They are incredibly difficult to control. The core problem is that you can't just throttle the fuel flow. Thrust depends on a complex dance between airflow, combustion, and pressure. Push it too hard by adding too much heat, and the engine suddenly unstarts. As you can see in this graph, thrust increases with heat flux, but then falls off a cliff. This sudden failure is exactly what you don't want happening on a hypersonic vehicle. So, how do you control an engine that lives on the edge of a cliff? The researchers' answer was to build a smart, learning-based controller. Instead of needing a perfect physics model, this controller uses an algorithm called RCC, which stands for Retrospective Cost Adaptive Control. Essentially, it learns on the fly, constantly measuring the engine's thrust and updating its own strategy to match a desired output. First, they tested it in a simple scenario, telling the controller to hold a constant thrust of 600 newtons. As you can see, the controller quickly adjusts and locks onto the target, demonstrating it can learn to tame the engine. But what about when conditions change, like they would in a real flight? The researchers then tested the controller against a wide range of different airspeeds, temperatures, and pressures. Remarkably, in every case, the controller adapted and successfully regulated the thrust to the desired level. For the ultimate test, they integrated the engine and its new AI brain into a full simulation of a missile intercepting a target. In this scenario, the missile is maneuvering, meaning its speed and altitude are constantly changing, creating a chaotic environment for the engine. And here are the incredible results. The missile successfully intercepts the target. But look closer at the thrust graph in the middle row. The blue line is the commanded thrust, and the black dashed line is the actual thrust produced by the engine. Even as the missile maneuvers, the controller keeps the thrust almost perfectly stable, something that's critical for the missile's guidance system. So let's recap the key points. The researchers developed a computational model of a solid-fuel ramjet, complete with its critical failure point. They then designed a learning-based adaptive controller that could regulate the engine's thrust without needing an explicit model of its complex physics. This controller proved to be robust across a wide range of conditions and, most impressively, kept the engine stable during a dynamic missile flight simulation. This work demonstrates a powerful way to make these simple but uncontrollable engines reliable, paving the way for their use in future hypersonic aircraft and defense systems.